Hello friends, in today's lecture we discuss about some reactions of cyclohexyl ring system, and in that case we already discussed some reactions regarding that. In previous lecture we discussed some reactions. In that reaction, first we take an example of some sterically hindered reaction. In that case, some 1,2-di substituted cyclohexane we take as example, and in another lecture we take some examples of tosyl chloride and methyl and neomethyl chloride. Okay, and in this lecture we discuss the next reaction called SNI. Okay, in SNI mechanism, or we write SNI reaction. In SNI reaction we can carry out some reactions. Suppose we take this example. This is the cyclohexane, and on that cyclohexane ring we have a ortho amino group. When that amino cyclohexane reacts with nitrous acid, at that time we get here the equatorial alcohol, or cyclohexanol having hydroxyl group is also present on the equatorial position. So in this case we can say that in SNI reaction, if the removal of NH2 or removal of nitrogen from equatorial bond, an exact position is occupied by the incoming group, which is hydroxyl. So how that is possible we can see here. HNO2, at that time it will convert into simple cyclohexanol. So this is amino cyclohexane simply convert into the cyclohexanol in presence of nitrous acid. This is one of the simple reaction, but in this case we get here both the substituents on the same position. Both the substituents on the same position. So how it get? Okay, so here when equatorial amino group NH2 is lived, and on same side OH group is inserted through cyclic 4-membered intermediate. So this one point is important for us: cyclic 4-membered intermediate. So we take an actual example of this. Okay, now first we convert that amino in presence of HNO2. We simply get what we get here, N triple bond N. Okay, now nucleophile OH minus first form bond. Suppose nitrogen carries positive charge. This is one nitrogen which carries positive charge. Okay, we wipe out these two words for our convenience. Okay, see here. And lone pair from this nitrogen will abstract this proton, and also this oxygen will first attack on this carbon atom, and when this hydroxyl group in close contact with this N2, at that time it will create some bonding with the nitrogen atom. So we see here how that bonding or how that four-membered cyclic intermediate is formed. Now we write here, these are two nitrogens. One nitrogen carries positive charge, and here we write oxygen, and here the partial bond formation in between this, and here also this oxygen will interact with this nitrogen, and here your hydrogen. Oxygen also carries positive charge, and we get here, this is the four-membered cyclic intermediate, 1 2 3 4. So here we write four-membered cyclic intermediate. Cyclic intermediate. So that intermediate is short-lived. That intermediate is very short-lived, and so that it will get converted by losing N2, nitrogen gas, and we get here a final product, cyclohexanol, by removal of this nitrogen. Okay, so this cyclic intermediate is very important to get this type of hydroxyl group which is also present at equatorial position. Okay, so we remember here in SNI mechanism, the same position which would leave the leaving group is occupied by the any incoming group. Okay, any incoming nucleophile which can occupy the position of the leaving group. Okay, so in next reaction we take another point, pyrolytic elimination. Okay, next point is pyrolytic elimination. So we write here pyrolytic elimination. See here, pyrolytic elimination. In pyrolytic elimination, one thing is very important to remember, which is in this elimination in this elimination we require the cis geometry. Cis geometry is required to both eliminating groups. Cis geometry is very important. In this case, I can focus on this point. Why? Because we can discuss some points in last lecture having the requirement for the elimination is transdiaxial. Actually, in ordinary examples, we can see the transdiaxial geometry is best for the elimination, and faster elimination reactions are carried out in that case. But now, in this example, this is one of the exceptional case for elimination, and here we take a cis geometry is important and required for the eliminating groups. So the faster reactions are carried out. So this pyrolytic elimination is one of the exceptional case in elimination. So here we take one example. We take an example of if the group present or substituent present on that cyclohexyl ring system, which is xanthate, group, then acetate group, then nitrogen oxides, and so on. Okay, so xanthate group is important. Okay, and now we take example having xanthate. Okay, so suppose we take another substituent having phenyl group, pH, or we write C6H5. Here this is oxygen, this is carbon, this is sulfur, this is another sulfur, and this one is the methyl group. Okay, so this is our bulkier substituent, which is xanthate, and in that case we write here this is a trans conformer, trans equatorial. Okay, and another case transaxial. We write here, suppose this is phenyl which is present at the axial position, and also this xanthate group which is present at axial, which is at the alpha position, and here this is the SME. Okay, now what are the product from both of these? Okay, here we already seen the pyrolytic elimination requires cis geometry, and here this proton from this carbon atom which is abstracted, and this eliminating group proton and this xanthate group both are having cis geometry. Okay, and in this case also we see this is your eliminating group which is proton, and this is xanthate group, both are having same cis geometry. So elimination is possible, and we get here a same product or single product from this both the conformers. So we write here this is transaxial, or we write transdiaxial. Okay, so how that elimination is carried out? This bond shifted here, there is formation of double bond, this bond will break, then this bond also break. Okay, we write like this, bond rotation, and this bond will also break, carbon sulfur. And in this case also that reaction is carried out. Okay, we write like this, bond rotation, and here the final product we get, or a single product we get from both of these conformations is this one. Here we write pH, then another substitute, then another product we having OCS plus CH3SH. Okay, so these three product we get, but our main product is this one, and we call this is 1-phenyl cyclohexene. 1-phenyl cyclohexene. Okay, so this is one of the important point here. Okay, so how that product we get having double bond or having a single product from this both the trans axial and axial equatorial substituents. So this geometry is required for pyrolytic elimination, and that elimination is carried out by using a 6-membered cyclic intermediate, and that cyclic intermediate is important in this reaction. Why? Because in other type of reactions there is a requirement for elimination is transdiaxial, but in this case we require cis geometry. Okay, so how that cyclic intermediate is possible? Okay, we see here only that cyclic intermediate which is possible. Okay, suppose this is your phenyl, this is hydrogen, this is oxygen, carbon, sulfur, here Me. Okay, so here 6-membered cyclic intermediate we have, 1, 2, 3, 4, 5 and 6. Okay, all these 6 elements or these 6 atoms are involved in that 6-membered cyclic intermediate. So we try to convert that cyclic intermediate into the, or this hydrogen will interact with the sulfur and we get here such a type of cyclic intermediate, due to this hydrogen is very close to the sulfur, and this is only possible when these substituents are come close to each other. And how that come close, or how that close to each other? When they are present in cis geometry. Okay, so here we try to convert that structure into the chair conformation. Okay, this is first chair, this is phenyl ring, and here first we write a chair. Okay, here this is hydrogen. I would like to write that bond by dotted line. Here this is a sulfur and having one methyl group. I write here this methyl at equatorial position. Why? Because that is a stable position. Then next is the carbon having carbonyl. Sorry, this is sulfur. Here we write oxygen. Okay, all these bonds we write by dotted line. Why? Because all these are broken. Okay, this is also a ring. Okay, so this is 6-member cyclic intermediate. Okay, and this cyclic intermediate we get very easily by the cis geometry and not by the trans geometry. If both of these groups are present, transposition at that time that doesn't come close to each other, and so that such a type of cyclic ring system or cyclic intermediate which doesn't possible. So for getting this we require cis geometry. Okay, and this is also possible. This is one of the example as a xanthate is our substituent, but when we carry out that reaction by using acetate as a substituent, at that time also we get such type of a reaction. Suppose this is your phenyl group, and here at the cis position we get such a type of intermediate. Okay, at that time also we get this type of cyclic intermediate, and we get a simple product from this. And what is the final product of this reaction? We write here so we try to rotate some bonds. Suppose this hydrogen carbon bond break, this carbon oxygen bond also broken, this bond is rotated here, and this bond is broken, carbon sulfur, and we get here a simple product having this is phenyl, which is present on sp2 hybridized at this condition or at this condition, or in the starting material that carbon is sp3 hybridized, but now here there is formation of double bond, so that carbon atom is sp2 hybridized, so that we can't write its actual position. This is the pseudo axial or pseudo equatorial, but now in this case here this is this is the actual axial position. Okay, now we get here 1 phenyl cyclohexene. Okay, so this is your final product. Okay, you remember in pyrolytic elimination cis geometry is must for elimination. Okay, thank you.